Good morning all. Today again we are going to meet discussions for this fluid mechanics on machinery. Okay, so this section is to be devoted for the course outcome 2. So we are going to that's analyzing the flow through the pipes and also interpreting the concept of development of boundary layer. So we are going to see what is meant by boundary layer. Okay, now this is the second unit, so flow through circular conduits. So we are going to see the basic concepts in this unit also, and also we'll be seeing so what is meant by boundary layer, so how it is formed, everything else will be seen here. So what it is actually, how this boundary layer is developed. See, you can see that the drag on a body is passing through your fluid may be considered to be made of two components. See, your body is in space and this drag on this body has two components. The first one is the form drag and another one is skin friction drag. So what is meant by form drag? This will be dependent on the pressure forces acting on the body, and another one is skin friction drag will be depending on the shearing forces which is acting between the body and the fluid. Again, I repeat, this form drag is dependent upon the pressure forces, and the skin friction drag will be depending on the shearing forces that act between the body and the fluid. Okay, so next, what's meant by actually shear forces? That's we know very well. The example is actually you can see that major losses in the pipes, that's due to the shear forces. You can take it as viscous drag, it can be a frictional drag, okay, it can be a skin friction which is caused by the shear between the fluid and the solid surface. So it will be the function of the surface area and the length of the object. So what about the pressure forces? For example, you can say it is a flow expansion losses. So that's called as a pressure drag or form drag. So why it is caused actually? It is caused by the flow separation from the body. So this is actually a function of area normal to the flow projected area. Okay, so that is actually a pressure force. Next one is a description of boundary layer. So you can see that you do have here, okay, and you can see this velocity gradient, how it is. So this is in the immediate vicinity of the boundary surface. So what is happening? So the velocity of the fluid goes on increasing from 0 to the boundary surface to the velocity of the mainstream. So this area or this regions we call it as a boundary layer. So there is a larger velocity gradient and there will be an appreciable shear stress. So tau is equal to nu into dou u by dou y at y is equal to 0. So the nominal thickness of boundary layer is defined as the distance from the boundary when the velocity of fluid is actually how much? 99% of the free stream velocity is actually somewhat equivalent to the free stream velocity. So that is called as the nominal thickness of boundary layer. Next one is actually we are going to describe what's a boundary layer. So it consists of two layers. So close to the boundary, okay, so close to the boundary we do have a large velocity. In the close to the boundary we do have a large velocity gradient and there is appreciable viscous forces. So outside boundary layer, so we do have the viscous forces are negligible and the flow may be treated as a non-viscous fluid. Okay, so again the shear stress, how it is actually, tau is equal to nu into dou u by dou y. So the shear stress that is acting on the plate surface what will happen? It will set a shear force which will opposite the fluid motion, and what will happen? The fluid will become decelerated. Since the shear force is opposing the motion of fluid, what will happen? The fluid close to the wall will be decelerated. So we have to understand the concept of boundary layer because it is very important to determine the velocity gradient and also in determining the shear forces on the surface. So we can see how the boundary layer is developed. So we can see that the boundary layer thickness will be increasing as the distance x from the leading edge is also increasing. So why? Because this happens because the viscous force will be dissipated more and more and the energy of the fluid stream will be proceeding and large group of particles are slowed down. Okay. In the laminar boundary layer, how it will be? The particles will be moving along the streamlines. and the disturbance in the fluid flow in the boundary layer is amplified and the flow will become unstable. Okay, so when the flow becomes unstable, what will happen? The fluid flow will be undergoing a transition from the laminar to the turbulent flow, and this regime we call it as a transition regime, where there is a shift from the laminar to the turbulent flow. Please see the diagram. The first one is actually a laminar boundary layer, and the second one is actually a transition region, and the third one is your turbulent boundary layer. You can see the turbulent layer and the overlap layer. You can see that it's buffer layer, viscous sublayer. We do have many. Okay, so after going through the transition zone, what will happen of infinite light? The flow will become completely turbulent, and will have the flow will be three-dimensional. Random motion of fluctuation will be induced. Okay, so this laminar boundary layer profile will be a parabolic, but in the case of a turbulent boundary layer, the profile will become logarithmic. Okay, that's very important. And this boundary layer depends on the Reynolds number, and it also depends on the surface roughness. So surface of the roughness will add to the disturbance and hastens the transition. Okay, so if the surface is very rough, what happens? The transition from the laminar to turbulent will be very easy. It will be very turbulent, in the sense it will be taking place at a faster rate. For laminar flow, we know very well tau is equal to nu into dou u by dou y. But in the case of a turbulent flow, tau is equal to nu plus eta dou u by dou y. So eta will have it as a eddy viscosity and will be larger than nu. Next one is the boundary layer thickness for laminar and turbulent. So when you just think about the boundary layer thickness, it will be governed by parameters like incoming velocity, kinematic viscosity of the fluid, etc. For the case of a laminar flow, we have it as dou is equal to phi. That is this formula. This is actually for the terminal flow. Okay, phi x divided by root of Reynolds number. Okay, this is actually an exact solution. And when you take it as for turbulent, this also for Blasius equations, we have it as 5.835 x by Reynolds number. And for turbulent flow, we'll have it as 0.3277 x divided by 1 by 5 of the Reynolds number. That is it will be the square of 1 by 5. Okay, so it will be actually the root of 1 by 5 for the Reynolds number. You can see the flow patterns, how it is actually is very close to the surface, the plane surface. The flow will be remaining laminar and the linear velocity profile can be assumed. Okay, and in this region the velocity gradient will be governed by the fluid viscosity, that is dou u by dou y is equal to gamma by nu, tau by nu. So that you can see this, please see the diagram, the eddy formation in the boundary layer, and you can see the free stream. Okay, the downer layer we can see laminar or viscous sublayer, and the upper limit layer also we can see. And actually the flow patterns and regimes within laminar and turbulent boundary layer. The case of turbulent flow owing to due to this random motion of the fluid particles, the eddy patterns will be set up. You can see that. Okay, so what happens, which will be small masses of the fluid will be sweeping up and down, and it will be moving in a direction perpendicular to the surface and the mean flow direction. Okay, you can see the diagram. And actually conversely, the slow moving fluid is lifted into upper levels, so slowing down the fluid stream, and by doing so effectively thickening the boundary layer, and there will be a rapid growth of the turbulent boundary layer. And also we do have it as a turbulent boundary layer we are having. Okay, so that will be the reason for this. Okay, you can see the diagram. Please see the diagram, you can see that. Okay, now what happens actually, next one. This is actually this diagram, you can see owing what happens to the eddies. Okay, due to the eddies, what will happen, fluid from the upper high velocity area is being forced into the fluid slower moving stream above the laminar sublayer. So what will happen, there will be an increasing local velocity because due to the here relative to its velocity in the laminar sublayer, because the fluid from the upper higher velocity is forced into the slower moving stream. Okay, so in order to explain the process, the eddy viscosity velocity should be added to the shear stress. So only you are adding it because there is some velocity variation due to this eddy. Next one is effect of pressure gradient on boundary layer development. What is it actually? The presence of a pressure gradient dou P by dou X effectively means a dou U by dou X term. That is, the flow stream velocity changes across the surface. You can see a curved surface. See the diagram how it is. The dou U by dou X is actually greater than 0. Okay, when it is increasing, and the pressure will be decreasing, and there will be a pressure gradient. But on the other side, you can see that the velocity is decreasing and the pressure is actually increasing. So you can see the velocity gradient. What is the effect of pressure gradient actually? If the pressure decreases in the downstream direction, then the boundary layer tends to be reduced in thickness, and in this case we get a favorable pressure gradient. Okay, what happens if the pressure increases in the downstream direction? The boundary layer will thicken rapidly, and this case is referred to as an adverse pressure gradient. So you just see you are placing a cylinder in a cross flow. Okay, so conditions will be depend on special features of boundary layer development, etc. So we can there will be a stagnation point, separation, as well as transition point from laminar to turbulent. Okay, so stagnation point, what it is actually, it is a location of zero velocity and maximum pressure. After that we are having a boundary layer development under a favorable pressure gradient. So what happens? In acceleration, there will be an acceleration of the free stream flow. So as the rear of the cylinder is being approached, what happens? The pressure should also increase. Hence there is a minimum in the pressure distribution P of X, after which the boundary layer development will occur. So after this P of X only your boundary layer will be developed and occurs, which the reason is adverse pressure gradient. Okay, you can see that the dou P by dou X is greater than 0, that is the pressure is increasing, and dou U by dou X is less than 0, that is your velocity is decreasing. You please see the diagram. So this cylinder in the cross flow, how it is actually, the separation occurs when the velocity gradient dou U by dou Y reduces to 0 along Y direction. You please see the diagram. Okay, so you can see the separation point and also the flow reversal. Okay, so this is what the location of separation depends on the boundary layer transition. Okay, so what happens actually after the separation? It will be accompanied by the flow reversal and a downstream wake. So thanks for your listening. So we'll be continuing this concept in the next section. Thank you all once again.